Thanks, everyone. I'm Saksham. I'm going to be talking about Python bindings today. There's going to be some amount of philosophy, hopefully a very little amount of Python, and some interesting C++. So let's get started. So a quick intro. I'm a quant research developer at a high-frequency trading firm called Tower Research Capital. I develop low-latency trading systems in C++ and research systems in C++ and Python both. I like performance software, clean APIs, and I like using these two languages to make that happen for me. So thus this talk. Hopefully more people can appreciate the combination of Python and C++. So first, why do we even talk about Python? Why not something else? I mean, there's a bunch of good things about Python. Like, it's low boilerplate. Like, if you have to write like some very simple business logic, have some metadata in a JSON, move things around, do all those things, it's really simple to do. Usually very understandable for most people as well. Also, it has become kind of a domain-specific language for some people. Data science, machine learning being the hot new thing. And there's lots of people who are pretty good at Python, so it's good to expose that. It's easy to use for a lot of people. I guess, not to belabor the point, but there are some very interesting and user-friendly tools that the interactivity of Python kind of helps us develop, use, like IPython or Jupyter Notebooks, if you guys know what they are. It makes it really easy for domain-specific users to be able to like just play around with the language. So it's a pretty good language to expose an API in. While C++, I mean, don't have to say too much about that. So specifically, when you are operating in a world where, let's say, you're writing a library and you're targeting some users that might be domain experts in something else, usually this ends up happening quite often. I have written C++ software, which people quickly reject until you make a Python API around it, even if it's a very simple shell. So I guess we should try to do that. Why should we just not have a shell kind of wrapper around Python? Just, write things onto std out, some Python process can read it, just the usual thing. Or just re-implement your code in Python. Obviously, you don't want to re-implement. You also want performance. You don't want to just write a really complicated matrix multiplication with Python loops. You may also have a library that's interactive with the user. Like, the user calls a method on it. It does something. Maybe it talks to some network databases or whatever. It gives you some result. The user transforms that result, goes back. It's kind of nice to have that like in the same process. I can go on and on, but I think it is a reasonable point to have a library that behaves like a native library in a language. So how do we do that? There's a lot of open source solutions for this. I specifically am going to talk about a subset of these. Feel free to look them up or talk to me about any of these solutions after the talk. Every solution has their pros and cons, but there's a surprisingly wide variety of available solutions to do this Python C++ integration. So without wasting too much time, I guess, wait, where's my, yeah. I guess let's try a hello world, see what we're even talking about. That said, hello world does print to std out, and I like micro-benchmark, so I have a different hello world here. It's going to be something very simple, just an increment function, a function that takes an integer, increases it by 1, and returns that. A very simple function. I don't even have to write the function body of that function here, also because I was micro-benchmarking, so I kept that in a separate translation unit. There's some code to profile how long it takes if you run it for, let's say, 1,000,000 times or whatever. I guess this should be simple for everyone. In Python, the same exact thing looks a little like this. The function is simple. And that brings us to our first look at some alien code. We have this thing called PyBind11, which seems to have some macros, I guess. That's what it looks like, a macro, right? And we are kind of exposing some CPP increment function pointer under the name increment and some, well, doc string called, which describes it as the incrementing function. So all I did is, well, these couple of lines. And if you compile that file into a .so, along with all the build dependencies and everything, you can kind of import it in Python as if you were just importing a regular Python library, and you can call that function. So that seems like surprisingly simple, right? Well, there's two of those. There's another library that I like to use, which is Boost Python, and it also looks very similar. And I guess the API also looks the same in Python. So what is this? What happened here? Like, Python seems to be an interpreted language. So how did we end up adding our C++ functions into the Python, well, memory space? Let's put it that way. Enter CPython. So CPython is the, well, the actual name of the binary that we invoke by calling Python, which most people would be familiar with, like the Python binary that you use. It's called, the actual software is called CPython. It's a C-based implementation of the Python language. Yes, it is entirely in C. Now, what does an interpreter have to do to allow you to interpret the Python language? It needs to read some instructions from you. Maybe you're typing them out in your terminal, or maybe you wrote them in a Python file and you ran that script, right? So it needs to maintain some state. Maybe you created some big lists, dictionaries, JSONs, whatever. So all that state, it maintains in something called a PyObject. Every new statement it reads just describes how to modify these PyObjects. Something like this. It reads some myfile.py, let's say. It can print stuff out to stdout. It can talk to other external built-in libraries, which, surprise, surprise, are also similar to the Hello World library we just wrote. So this is the core of the CPython binary that most people just know as Python. Now, if we wanted to extend this and build our own C++ features into this thing, for instance, someone wrote the HTTP, let's say, or the socket programming stuff for the CPython thing, right? It's not just pure manipulation of internal state. It has to do some like syscalls and all that stuff. So someone probably built some module for this. That's exactly what we are also doing here. What we're doing is we're probably building our own .so or module whose job is to talk to these PyObjects. And it can kind of register into the interpreter. For instance, earlier when we did the increment function. So we just told the interpreter that if someone calls the increment function, you have to invoke this function pointer. And it might actually give you some PyObject references or pointers along with that increment function. In this specific case, you would probably get a PyObject that has the integer that you wanted to increment. And then some black magic makes that integer go from a PyObject to an integer, so you can work on that object inside your C code. So that's roughly the gist of what we're doing. This lib hello.so is the thing we will be implementing. And, well, that thing, like this module that we built, I'm going to call this, not I'm going to call this more like, we call that an extension module. Python is a fairly well-established language, and these extension modules have been used since ages to, well, extend the language. We write these extension modules using, well, earlier I showed you examples with Boost Python and PyBind. Under the hood, what's happening is Python exposes a C API, which is in this header, python.h. And everything we're doing is essentially translatable to some function calls that are present in python.h, like including registering the function into the interpreter state so it can call that function pointer when you invoke the function. Now, to strip away the details of, to strip away the syntactic sugar and look at the details of how that C API actually looks. Don't worry, you don't have to read this. People rarely have to write this nowadays. But in reality, if you did not have Boost Python or PyBind, you could still do everything. You would have to include this python.h header. You would have to manually parse out those Py objects into integers. You would have to convert your result integer back into a Py object. You would have to register your module into the interpreter. You have to do a bunch of different things, basically. And thankfully, we don't have to really do this unless we really want to. But yeah, it is a little verbose. Cool. So hopefully, are there any questions? So do people at least understand at a high level what CPython is and what we're doing here? Cool. There's nothing special about C here, though. You could have just written the Python interpreter in, let's say, Java or C#, and people actually did that. Just a quick minor note. If some people wanted to write their extension modules in Java or C#, so they rewrote the Python language interpreter and called it Jython or IronPython. And, well, just a quick, yeah.
There's also one being developed in Rust.
Oh, OK, of course. That seems like a reasonable thing to do at this point in 2023. Yeah. So yeah, quick digression. Yeah, there's nothing special about C. It's just the most widely adopted one. It's the canonical implementation, so that's why we're talking about it. So at a high level, I wanted to have a slide that just describes all the different extension module solutions available in this ecosystem. We are going to be talking about those two primarily, like this kind of stuff, where you, as a C++ library author, have a million lines of C++ code. You probably wrote some software about it. You probably compiled an executable with it. You maybe have some C API for it, and you want to do the minimal amount of work to make it available to users in a performant fashion. There are other solutions. The most popular one is actually Cython, which, it's hard to classify it under any of these things. It also falls into the pre-written C++ code section. We'll talk about that later. Some people decided to take the just-in-time compilation approach to speed up the Python code. There's Numba or PyPy for it. They're pretty helpful if they fit your particular use case. There are some other things like CPPYOI, and obviously you could also just write that manual code, the Python C API code that I showed earlier, this kind. So that also works. But we primarily will be talking about the stuff that's relevant to, let's say, a C++ library author. Yeah.
I'm assuming Cython up there twice is intentional.
Yes, I could have also put it in pre-written C++ code. Okay. It's just hard to classify Cython. We'll get there. I have some examples about that. It's pretty helpful and nifty. So we expose one simple hello world function. Before we start building complex software on top of this, I do want to take a minute to discuss the different overheads of this so we can actually choose whether the solution fits our use cases or not. There are two primary use case overheads that you might imagine in that very simple example that I shared. One is just the cost of invoking a function, and B is the cost of converting your arguments from Python objects to C objects, and then back from C objects to Python objects. So these are the two overheads. I did not distinguish between the two because that example was pretty simple. That said, it is a micro benchmark, so take it with a grain of salt. Here's an illustrative image of a grain of salt. Well, so moving on. Here's a rather interesting table. I profiled all the different implementations that I showed earlier. Ran it once. Once obviously is pretty meaningless. I guess the 1,000 runs one is closest you would get to a reasonable micro benchmark result. C++, obviously, 1 nanosecond, everything is just like in the hot path. Oh, sorry, everything is in your cache, L1 cache most probably for everything. So it's just like looping over that very small loop, like 1,000 times. Python, 67 nanoseconds, much faster than I expected. just calling a Python function in a for loop. Given that there is no just-in-time compilation, that's still pretty good. Python C API, 74 nanosecond. I just chalk it up to noise. I think it's just probably the same as Python. PyBind 11, by far the slowest, and Boost Python, close enough to Python. So these are the numbers we're talking about. I'm not going to comment too much about the relative difference. I do want to focus on the fact that roughly, if you're willing to pay 100 nanosecond per API call, then exposing your APIs between the C++ Python boundary seems like would be a possible solution for your use case. If you're not OK with 100 nanoseconds, then probably you should consider something else. So that seems like my takeaway from this particular table or micro benchmark. Quick note about PyBind, it's slow because it seems to be doing some mallocs internally. It allocates a vector for all the arguments, even though you're passing one argument. And it seems to be doing some extra typecasting work. That's what I inferred based on reading these GitHub issues. Other people have also observed this overhead. I personally have used Boost Python much more than PyBind, so most of the talk I'm going to use Boost Python syntax, but they're not that far off. Yes?
Maybe potential comment. I do know that every time you pass a vector from Python to, or from C++ to Python, for PyBind at least, it converts it to a list. So that, I don't know if that's exactly what you're talking about here, but.
So there are two things. So I will come to that particular thing later. It's one of the more interesting parts of this presentation. But right now, I think it's more of a factor of, let's say, the function the increment function takes an integer as an argument, right? Mm-hmm. So the Python bare bones API for parsing arguments, like for implementing a function, it has to do some argument parsing like that. It doesn't really know that I'm getting one argument because you're free to call multiple function with multiple arguments. And there's some like parsing logics that you have to implement inside the body of your function. And PyBind's parsing logics use a vector, even though there's one argument expected. So that seems to be what I inferred from those GitHub issues. I am happy to be corrected. I would also love for PyBind to provide a more efficient alternative here. That said, most people try to not care about the 500 nanoseconds here. The authors of PySimD.json actually did care. They dropped PyBind 11 and moved to Cython. Well, so now that we have the performance numbers out, we know what kind of solutions this might be useful for. Let's try to expand our vocabulary a little bit. Classes. I'm going to illustrate this with a kind of real-world example. Like I have some like weird form of binary data that I was reading. It's split into rows, but each row can have like multiple items in there. Each item is like name, comma, value, something like that. It's not really columnar data. So I had some binary data reader to parse that data and listen to it and populate some vector of rows. So this is a simple example, but as, let's say, a software engineer, you might have built a much more complicated system which computes some data like this and stores it in memory. And now you want to expose these rows in this particular case to the user. So how do we go about doing that? Like this code is pre-written. Like this is not code that you would write for your Python thing. Like this is stuff you already have. So to declare this stuff to Python, to define the Py bindings for this, let's say, you kind of write a code similar to this. And I expect this is mostly readable. This is Boost Python code. PyBind looks similar. You say, oh, I have this class row. Please call it row inside Python. It has an attribute nanotime, and it has a method items. There's some stuff later that we'll get to eventually. But this is basically how you declare a class from C++ to Python. We'll dive into this as we go along. I also defined a vector of row, and I told it that, OK, there is some utility called vector indexing suite. You can use that to expose this vector of row to Python. And then I declared my row reader class because it has this getRows method. That's the user-facing API here. And everything else is not user-facing, so I'm not even bothering to inform Python how to call those functions. But get rows I had to, because that's what I expect the user to do. I expect this code to be used like this. You create a row reader with a test file. You get the rows. You print the length. You print the row. Like, this is the most simple example. This is the base case study that I'm going to use to illustrate different powerful utilities that we have here. OK, so what happens when I wrote that entire Boost Python class code? What Boost Python does is it registers these two functions called from Python and to Python for every type that you declare. So let's say I declared this row reader class. It's going to generate some from Python and to Python functions to convert between a Py object and your C type. So every time you're communicating between your Python interpreter and the code you wrote in your C++ files, these are the intermediate functions that are coming into play here. It already has these converters for, let's say, integers or vector. We had to explicitly write it out, but integer, strings, like those things kind of work automatically. OK. Proof that it works. I have a compiling example. You can run it. I have a slightly domain-specific example here, but this is some garbage data. It's like there's some timestamp for the row, and each row has some items, some random trades, prices, some garbage data that's I actually generated this with like a rand call. Anyway, seems to work. Now, before we make this more complicated, now that we have all the building blocks, we know how to expose functions, we know how to expose classes. How do we design our APIs? The basic thought process is you have to draw a line between the user API, the user-facing stuff, and, well, your C++ code. So once you do that, you can start exposing functions at that boundary. And what most people end up doing is, especially because they don't want to pay these 500 nanosecond overheads, let's say, they try putting the hot path, or the code that's invoked most often, inside the library. So rather than have the user loop through, like, let's say, something with 100,000 function calls, you would probably just put those 100,000 function calls inside Python. So that's the high-level goal of designing any API that's going across these like language boundaries. Sometimes it might be easy to expose a hot path API. Sometimes you might have to design like a whole new domain-specific language, let's say. For instance, yes, people could have written, let's say people want to implement neural networks. They could evaluate the neural networks by hand inside Python, but that would not really be an optimal solution. You would rather just take the neural network object inside, let's say your, I guess I'm like talking about any machine learning library, let's say PyTorch. So you would rather have the entire network, all the weights, everything inside the C++ code, evaluate that, and just return the output, rather than have the user write that for loop code in Python. So there are DSLs for this, like even computing the mean of, let's say, a very large array. You don't want to be adding like 10 million integers in Python. It's going to take 10 seconds. Also, you could define, you could allow Python objects to just flow to your C++ library if you wanted to. They're not too hard to deal with. They're like annoying to deal with. If you can cast your Python things to integers and strings and all that, that's usually nicer. OK, I guess we already discussed most of this, but ideally you want your functions to be set up, getting the result, or doing like a very complex operation inside a hot loop, and that's pretty much it. You don't want your functions to be usually in the hot loop. And when I say hot loop, I just mean hot path, or like the code that's executed the most frequently. What arguments should you pass on, put on the boundary of Python and C++? Primitive types, int, float, vectors of strings. Most things work. Boost Python, PyBind, they're going to convert these to your native types for you. You ideally don't want to care too much about the performance if these types are on the constructor, or let's say the result getter side of things, and they're not too big. You do want to care about them if They're in your critical path of your code. You can also just have Python objects in there. Why would you want to have Python objects as an argument to a function? Because your function is in C. I found one use case, like I had this like reader class, and it takes this thing called file names as an argument, and I wanted it to be a string or a list of strings. In C++, I would have had to define like an std variant, and then I have to think about how to convert a Python list to an std variant and all that. I just take a Python object and check if it's a list. If it's a list, then I convert it to a vector. Otherwise, I just create a vector and push that string into a list. Yeah.
I believe PyBind does native conversion from anything to a variant, so long as it knows how to convert the thing to one of the variants.
Interesting. So that would be helpful, yes. I have not tried doing that with Boost Python. The documentation for Boost Python is rather scarce. PyBind's documentation is actually very good. Yeah.
I found it to be pretty good as well.
Yeah. All right. Finally, return values. Again, same principles apply. You can return Python objects if you want. As long as things are small, you don't mind doing that. You could have integers, floats. The binding library should do the heavy lifting for you. Except, what if you're returning large matrices or vectors? You already spent a lot of compute, let's say computing a million cross million, actually that might be too big, 10,000 cross 10,000 float vector, let's say, and now copying that into a Python data structure seems arbitrarily useless in this situation. You could return a vector of vectors, then have Python loop over it and convert it to NumPy. You probably don't want to do that either. Turns out there's C++ bindings for NumPy as well. Just taking a good, taking this opportunity to give this example, NumPy arrays are just like C arrays, almost with some extra frills around the corners. You could just construct the Python object inside your C++ code and return the Python object. And that seems to work out well enough for performance reasons, from a performance perspective. All right. Last topic before we get into a more interesting case study, lifetime of return values. Python is a garbage collected language, which uses reference counting. So if you try to return a struct like this, which has a raw pointer to something, this struct may end up having a dangling reference if you just return this thing. It's a classic textbook case for using shared pointers. If you use the shared pointer, as long as the struct is alive, this pointer, the reference would not be dangling. We will see more easier ways or cleaner ways to do this later. But, well, you could replace that with a shared pointer and things would be safe. All right. Finally, so what we're doing here is, with all of the stuff we discussed, we are trying to compose softwares, especially when a user and a library author are two different people. Composition between softwares is something that deserves some attention. Most C++ programs that are traditionally written, they use Unix, the shell, to compose. Like, you're used to outputting text onto an stdout, piping that, and doing all that stuff. I'm calling that a software glue, like the shell. And the whole premise of this talk is that Python is actually a pretty powerful software glue to allow people to manipulate results of your library and interact with the library in more powerful ways. Right? So before we dive deeper into that example, are there any questions? Yeah.
Maybe I just want to understand your point, what you think about writing it in Boost or bindings versus Cython itself.
Yeah.
Because I feel like writing Python with C++ bindings in C++ is less understandable than writing in Cython because it's more native Python.
Yeah, I agree. I actually agree to that. I do have some examples later where Cython makes much more sense. Usually, in my particular case, the reason I went down this rabbit hole like 3 years ago is, if you already have a huge library with like lots of build dependencies, everything, I have a complex build system, it's building a C++ library executable for me. Integrating that with Cython is a much bigger task. There are cases where Cython is very useful. Those cases involve when the functionality that you're talking about can be achieved by including a couple of headers and C++ files. So if your library is of the form of a couple of headers and C++ files, Cython works out pretty well. If it's much bigger than that, which in my case it was, it became much trickier to keep integrating that with Cython.
CMake does a wonderful job for that as well.
OK. I will talk to you about that after the talk. Yeah. All right. So it's the same. Now, going on to this, we'll explore a couple of questions we should be asking ourselves when we're exposing these APIs. I'm going to continue on that row reader example that I had. I had some binary logging data. I initially tried to, well, write out the parse data onto stdout, have Python parse it out. The users of this library wanted to write some analysis on top of it. They wanted to compute some statistics. And once you have that data in Python, they could easily do that. But it was too slow. Obviously, we are serializing, deserializing. We're losing type information. We're losing the memory adjacency of these objects. It's just arbitrarily slow. Also a good illustrative example. I wanted to just reuse my C++ library and expose that data into Python. So that's what I did. And here's that example. We've seen this before. We have also seen this before. This time I replaced some stuff to kind of start making us think about other stuff, deeper questions. For instance, the getRows function now returns a vector of row ref. I haven't really defined what a row ref is here, but maybe you want to be returning references to what copying. We'll think more about this very soon. OK, so this is roughly the same code I had earlier with some extra things that I did not define earlier. Let's break this down. I'll first focus on this thing. This is like the simplest 101 declaration of a struct with a method. Here, item is a struct. It contains an ID and a variant. And I wrote a function on it called getPyValue, which converts the variant into a Python object and returns that. And the declaration for this seems simple enough. The user can just call ID or value and get the key and get the ID or value as they expect. The second thing, which is something you alluded to earlier, is this particular line. So as I mentioned earlier, in this example, a row is made of items. It's a vector of items. Now, how would any binding library know if the items that you're returning, I'm using a const auto ampersand here, how would any binding library decide if you want to return a reference or a copy? Returning a reference as it is seems extremely risky because it's just going to lead to a dangling reference. It could copy it, but copying it seems could be expensive. Maybe we don't want to be doing those expensive mallocs because we're doing all this for efficiency purposes. So let's try to engineer the best possible semantics for this particular use case. I don't want to copy the items. I also don't want to have a dangling reference. First, what's the dangling reference I've been talking about? Let's say I have a function that returns the items inside the first row. Here, the row object goes out of scope once you return from this function. If you return a pure pointer, then your items vector pointer that you have would be pointing to something that got garbage collected by the time you exit this function. So this is obviously unsafe. It's called return existing object in Boost Python. I am not sure what it's called in PyBind, but you could tell the library that you want to return a pointer, but then you are risking things significantly because it's just going to make your API have unsafe pointers lying around. So, yeah.
To be fair, this can be a problem in C++ itself.
Yes.
With a full range of. Okay.
Yes, but
so maybe you want to translate the problems too.
Yeah, I think the more higher point that I'm trying to drive here, we have to design safe APIs without losing too much performance. So this API is certainly unsafe. It would also be unsafe in C++. So this is what we did. It's unsafe. I have an alternative proposal. What if instead of returning the vector directly, I returned something like this fused struct? It has I think I forgot to put an ampersand there, but it has a reference to the vector. And it could also keep a reference to, let's say, the row object that owns this vector. So in that case, as long as this row object, by the way, Pi objects they behave like smart pointers. So you manually have to increment and decrement their reference count because Python is written in C and not C++. But that's what I've done here with PyIncRef and PyDecRef. Not related, but you could translate that to saying that there's a shared pointer of the row in the struct. So if you had that, you would not have an unsafe pointer lying around. This seems nice, but hard to do for every single use case where you have a vector, and for everything you'll have to implement a struct like this. Seems painful. Yeah. Luckily, Boost Python has a nice shorthand for this. It's called return internal reference. What it does is if you call a method on something, let's say you call a method on that row object, and it returns a pointer, it creates a Python object that contains a reference to that pointer, as well as the row object that created that reference. So you're saying that I'm returning an internal reference to this row object, therefore, I want you to keep the row object alive as long as I have this internal reference in my Python code anywhere. So I found this to be pretty helpful. I have tried running this code, and it does not make copies or unnecessary. Like the memory usage remains the same, so it seems to work pretty ideally. And now we have a nice performant way to expose vectors to Python. On the topic of vectors, diving more into this particular line, what is this vector indexing suite that I mentioned earlier? I'm trying to inform Python that if I return a vector of item, I want you to call it cpp vector item inside Python. That's just for printing purposes. But I also want you to implement the semantics of this vector using this thing called vector indexing suite. What is this? So in C++, if you have a vector of integers and you want to modify that object, let's say you have a vector of some struct and you call .mutate on it, you don't expect to get reference semantics there. You expect to get value semantics with a vector in C++. Let's say you access, I think this example is slightly misworded here. Let's say you access the first element from a vector, and then you call .mutate on it, and then you go back to the first element of the vector. It would not have changed because the vector semantics that we expect in C++ are value semantics. This example could have been better, but in Python, that doesn't work that way. In Python, you could think of Python lists as having a list of shared pointers. That's essentially what most Python programmers expect their lists to behave like. Vector indexing suite just puts some wrappers around the stuff you're exposing to make it behave like a Python vector. So anyone who accesses square bracket 1 on your vector inside Python will just get a reference to the object inside your vector. So that's just what it does. It's to expose a consistent and user-friendly behavior for a Python programmer, so they don't have to really deal with C++ and Python differences. So here's this whole thing put together, the two different things we discussed, the vector indexing suite and the reference, reference internal object. I could change that. But if you do this, what I'm trying to do is I'm trying to get all the rows from my row reader into Python. I ran this on, let's say, a reasonably large data set with maybe when you loaded the row reader object, it created 500 MB worth of data. Once I save that data in Python, my memory usage remained the same because of the two different things we just discussed. None of this stuff is making any copies. We're just exposing some, maybe not the cheapest, but some thin wrappers around C++ memory. We're just exposing some Python functions that if the user calls square bracket on a vector that you returned, it's just internally taking a reference to the thing that you have and returning that and letting you operate on that without making any copies of large data structures in this particular example. That's also because my vector is a vector of shared pointers. I just switched to shared pointer here because of some other reasons, but yeah. All right. Finally, the last part of this particular example, the constructor. We have a class. We're trying to construct that with a file name. There's two high-level things I thought of, which people usually use while implementing constructors. They may throw exceptions because, well, I mean, I could do two-phase init here, but this seemed like a good enough place to talk about exceptions. You may also want to be reading the file across different threads. Obviously, the topic of threads introduces lots of other stuff to talk about. But first, exceptions. Exceptions are simple in Python. You just have to set a thread local variable using this function called pyErrorSetString. So I wrote some code to convert a C++ exception to a Python exception. Seems simple enough, don't have to think too much about it. One thing I do end up doing in my code is, so my C++ library that I've spent years working on is probably going to have some abort and exit calls for error cases in various places. You may want to make an ifdef around it to make it throw an exception instead of dying when you're compiling that library for your Python module use case. So I found this helpful. I didn't have to change my library too much. Yeah.
PyBind 11 has most, I think, or all standard exceptions built in.
Right.
You can add more.
Right. No. So yes. So that part, completely agree. Also, abort and exit, PyBind 11 won't handle.
Okay.
Yeah. So that note still sticks around. But yes. Hi.
What is the scope of the exception handler registration? Because it looks like a free function call there, right?
It's inside the module. So the
module scope.
Yeah.
Okay.
I believe I've seen a flag that allows you to choose where all it applies. I haven't needed the details of that, but yes, you can. We can look that up later after the talk. There are other scopes you can configure it for. Anyway, this is something I found very useful while converting my libraries. I did not have to go and change every single place I'm throwing in exit condition. Yes, if you already are throwing exceptions, then great. You don't have to deal with this. Okay, the most controversial topic, let's put it that way, threads. Yeah, oh, sorry.
The vector of shared pointer thing, that also applies to an object of other objects, right?
Object of?
Like an object that has other objects and returns them by reference.
So what's the part about vectors here? Oh, you mean the return internal object thing?
Yeah, and the vector of shared object thing.
Yeah.
That thing also applies to an object of that object that has other objects and returns them by reference.
Yes. Yeah.
So is there like a helper or something further?
I think this particular thing that I mentioned here, I mean, here the object has a reference to a vector, but it could have a reference to some other object. So I think this return internal reference thing just handles that. I'm not sure if I understand the question fully though. But basically this return internal reference is a pretty good semantic. Like, I mean, Boost Python calls it this thing. You could call it something else. I want to focus high level on the fundamental problem we're solving, which is how do you prevent dangling pointers in an API? And this is just one of the approaches that seem to make the most sense. And luckily, they have an easy API to do that. So, right, threads. What if you want to read multiple files in parallel. Like here's an example. I have multiple files. I want to analyze all of them. So the user wrote some Python thread API to run these different constructors in parallel and load all these bytes into memory. I tried this, and well, obviously it runs serially because Python has a global interpreter lock, which means that any code that's running does not like to let other threads run. So, yeah.
I'm not 100% certain on this. Do you know if the GIL is a CPython like exclusive thing? I don't know if that's actually like standard that it has to be.
It's not a part of the standard, but as of right now, there are very few, if at all, implementations. The one thing I did read is someone forked CPython to get rid of GIL. They managed to do it entirely, but it was so complicated that they never got it merged. And I haven't looked it up in like a year or so, but at least a year ago, that was the state that people were like, this is great. We have no idea how to merge this. It's complicated, the language. I mean, keeping things performant while making them lock-free, you have to deal with a lot of things, I'm sure. But as of the, yeah.
Python 3.11 will have no GIL.
Python
So
what? 3.11?
will have no GIL in it.
Oh, really?
If you don't want to use it, you can. And of course, if you're using Cython, you can just say no GIL and that works.
Yeah, which is exactly what we'll do here. So if you're writing your own library, so the GIL is there to prevent these Python objects from being manipulated by multiple threads, because the core of the Python runtime is not, at least up until 3.10, is not thread safe. Luckily, you can construct a simple RAII guard that you can put in any function, any scope that you have, and it will release the GIL. So actually, really simple, very helpful. Cython has this other thing called no GIL for this. Yeah.
PyBind 11 has this built in.
Okay. Actually, there are macros in python.h for this exact thing. So you just say release GIL, get GIL, something like that. I forgot what they're called. This is
threading.
Sorry?
It has something that's called allow threading. And,
yes, yeah. I don't use those macros. I like this thing more just because C++, but python.h is for C. But internally just uses those function calls. So I tried it on a test example with some large files. The user time remains roughly the same, but the runtime goes from 11 seconds to like 4 seconds, which is what was expected. Yeah.
So is this toggling of the GIL a global toggle, or is it only for like, is this just for like object within the scope of where you toggled it off?
It's for the thread that you're in. Yes. So okay. Whether you have the GIL or not is a thread local variable.
You can think of it as whenever you're calling into Python, it always assumes you have the GIL. And so then if you don't want it, for parallelism, you can release it.
Yeah. But if you release it and you access a Python object, that's unsupported behavior. Like it's probably going to mess up.
Okay.
Yeah. Just don't do it, segfault, whatever. Yeah. But very helpful trick to have under your sleeve. Okay. This basically concludes this particular row reader example that I had. Moving on. I think this would be more relevant to the general. This should be something that's more understandable for most people. Usually, let's say you're writing a HTTP server or you're listening to a socket and you want to do some callbacks. That's a general form of software libraries that people write where the C++ code takes over the control in a sense that that's where the blocking is happening. That's the one that's looping over. So how do you make the design decisions for exposing something like that to Python? Not a surprise. A lot of this is going to be about threads and GIL locks. So before I go on, I will be using this term called dispatcher. For our purposes, a dispatcher is something that just has some sources and it listens to them or blocks on them, and it has some callbacks that people register. If there is data on this socket, then please call this function. That's what a dispatcher is. When I say a callback is, let's say, a function Here is a very simple 5-line example. You have some function that just prints a packet, and you have a network library. And you say, hey, like, give me this callback whenever there's a packet, and block. Here's the most simplistic network library you can think of. Now, where is the blocking happening? Where's the dispatching happening? It could happen in the Python thread, but then you let the Python thread get blocked. Basically, similar to that row reader example, when you were reading the bytes from the disk, the Python cannot do anything there. It's just waiting. In this case, it'll wait forever. It could also happen in a separate thread, but then there will be other issues. Let's see what they are. Before we go on, callbacks are pretty simple. In C++, you can just accept a Python function. You can check that it's a callable, as in you can call it, and then you can actually just call it with parentheses. Boost Python makes it pretty easy to do that. I'm sure PyBind has some nice APIs for this. This is how I implemented this code. So now that we can do this, we know how to call Python functions from C++. How do we make the design decisions for this? So let's start implementing a web server that gives some callbacks step by step. Let's start with the simplest one that we just saw. You start in Python land. We have one single thread in this example, which is if you keep following the black arrows, those are the threads. You register some callbacks, go to C++, it saves some stuff, it checks that it's a callable, returns. Python says, hey, can you block and give me callbacks? And after that, the control is in C++. C++ is running a while true. It's going to wait until it gets a packet, call some Python function, go back to waiting on while true. It works. It's very simple. You don't have to think too much about threads and everything, but you cannot really do too much with this. You cannot have more worker threads, for instance, or you can't have your Python layer monitoring what's happening, what's your CPU utilization, printing some stuff. You can't have that code running in Python separately. So let's make this more complicated. So here's what I did. This time, the C++ layer now has some worker pool of like threads. And we let those workers call this Python callback handlers. What do you imagine would be the issue with this? Those workers are in different threads. The GIL, the lock, is held by this primary thread, the C++ one. So it is illegal for those workers to call the callbacks unless they acquire the GIL. You could also make the main thread join the workers. That's an inefficient choice. The other way to do this would be the more reasonable way to do this. When the main thread starts, it gives up the GIL, and it lets the workers take the GIL whenever they want to. So this seems to handle the complexity level 2, which I'm calling this. Seems to work fine. You can add as many workers as you want. You will be bottlenecked by how expensive the callbacks are. But that's a separate design debate, let's say. Since the main thread actually gave up the GIL, Python is not inherently blocked here. So you could add some stuff in Python, and you could move the C++ thing to a new thread. Like you could the C++ function could just launch a thread for itself, return, and Python is free to do, well, monitoring resources, logging information. So that's actually very helpful. Yeah.
Who owns that thread then?
Which one?
Spawn a new thread, return to Python. Who owns that thread we just spawned?
This my network library object that you had, it could probably keep a reference to that thread because that object is owned by Python.
Okay.
Yeah. So and it can internally keep a thread. Python could also just launch that thing inside a thread that it launched. But then the constructor of this, not the constructor, the while true thing needs to discard the GIL before it starts. But something has to discard the GIL, and those things have to take the GIL. And this is pretty nice. Now you can do something like while true, print resource usage, sleep for 10 seconds. It's very flexible. Can we make it more powerful? Are we still missing something? I say we are. What if this now freed up Python thread wants to interact with this my network library and mutate some internal state in there. Now we bring in thread safety for C++, not Python this time. Maybe the user wants to, well, here's an example. Maybe it opens a shell for the user, and the user can kind of control some internal state, which tweaks with these worker processes that are running in separate threads. This, I would say, is the most general design for like multi-threaded applications. People may want the functionality to be able to do that. How do we do this? One possible solution is to add locks into every internal C++ code that you're running, which seems rather heavy-handed because you shouldn't really penalize your C++ class for just being able to interact with the Python interpreter. What if you could make your C++ threads wait for some instructions from Python? I'm going to use the term dispatcher here because I'm assuming that these worker processes are being called by some layer that's watching some file descriptors and waiting for data to come up on those file descriptors, and then it's doing some stuff, right? So what if it was watching 2 file descriptors, and this other file descriptor could just be something controlled by Python? And it could be like, hey, please stop whatever you're doing, and I will pass a lambda to you, and please call that lambda. I call it safe dispatch in my code. You could call it something else. The Python layer could probably call a function like this, where there's a channel, which internally sets that file descriptor dirty and waits for the C++ thread to call this lambda, set some booleans, and you wait until that thing is done, and return the result. The way I use this is, let's say my network library has this subscribe method that's available to Python as a user API. I just do a safe dispatch of this internal subscribe function, and that seems to be thread safe. Now, I think we have achieved most of the thread safety we could be hoping for in such a scenario. And yeah, so these are the high-level thread-related topics that I wanted to discuss. Any questions? OK, we got this working. Finally. This is rather, you could call it a micro optimization, but I want to bring pointers into this whole thing. And this is also how I'll bring Cython into the discussion. So again, the same row reader analysis code that I had. The user wants to parse some items. They want to compute this toy statistic called sum signal change by trade size by looping over all the data. And they have some code to compute that by doing some processing. And I want to make this faster. This is the hot loop here. The user is writing the hot loop, which seems unfortunate. We are providing them a .so with some API. And they seem to have to do the for loops themselves. That seems sad. Did we just fail as an API designer? Perhaps. Maybe the problem is too generic. I don't want to necessarily say that you can always have a problem where you can expose the hot loop into C++ and the user will never have to write loops. That's not the case. That's not going to be the case. Do we just let it be slow? No. Let's try something else. So I'm going to primarily focus on optimizing this particular block of code, these 4 lines. So let's look at the for loops first. What's happening in the Python interpreter when it sees these lines is there's some bytecode, and each time it hits that line, it interprets that bytecode and it does some work about it, and then it calls a loop, like does whatever it had to do about it. Perhaps we could compile this code into an actual for loop, and maybe it'll be faster because it doesn't have to interpret the bytecode. Luckily for us, Cython does that. Cython is a binary that reads your Python script and converts it into an exactly matching C program that uses that python.h API to construct these by objects and do everything on them. Like this for loop, it would convert this into a C for loop but the rows and all would still be Py objects. So that's what's happening. So Python works pretty nicely for this thing. It compiles your for loops into C loops. It looks extremely complicated. It's not meant for user consumption usually. But if you look at the end, there is a while loop there. So that's nice. The performance does actually improve. In this particular example that I had, it went from 36 seconds to 34 seconds just in that hot loop. It still has to deal with the fact that it doesn't really know the type of any of these objects. So it still has to just do the whole machinery of Python to be able to retain the same exact semantics, because we allowed it. Python does not have types. Well, not compiler types. That said, this is the best we could get until this point. Now I want to focus on this other line. I have this reader object, and this has this method called getIdName. If you give it an integer, it returns a string. And then the user wants to do some logic on top of this. This getIdName is a Python function. It's going through that 100, 200 nano overhead that we discussed earlier. Now this is the micro benchmark that I'm going to present. What if you don't want to pay that overhead? You could do this for every single function that you have in your hot loop. I'm going to take this one simple example. What would be the what would be the most optimal way you can do this? Like get rid of this Python function overhead here. You know that this function corresponds to a C function or a C++ function. So there is a function pointer for this. It has a type signature. You know that because you wrote the library. Can you just get that function pointer and call the function pointer rather than go through the whole reader module, access the Python function, do the type conversions? Well, you can. And that's why I have an image of capsules there, which I generated with DALL-E. So, well, that's what a capsule is. A capsule is essentially a pointer that's wrapped inside a Python object. What do you do? These are the two important functions that we will use. It's called, you create a new pointer with a void star. You give it a name, and you get the pointer out of the capsule with a name. But these are C functions, right? You can't call pointer functions inside Python. Luckily, we moved to Cython earlier in this particular example. And Cython is pretty helpful in allowing you to just call C functions if you want to. So in this example, what I did is I called reader.getIdName function pointer, which returns a capsule, and I cast that capsule to the raw pointer type. Again, I don't advise doing this. This is a tool that you can use judiciously if you have an expensive function call in the middle of your hot loop. You don't have to do this. This is a micro optimization in this case. But it's very powerful. Because now you got this getIdName pointer and a self pointer to that reader object, because that getIdName needs to be called with an associated object. So you can call that function as if it was a C function, and you get a string out of it. That's pretty nice. I think we ended up getting rid of some function calling overhead. We also ended up getting rid of some type conversion overhead. Performance gets faster. I tried to calculate how much faster it got. It saved roughly 300 nanos in this particular example per function call, which is within the ballpark of what I expected it to be. It's ugly code, but you can use it judiciously if you want to. I skipped the slide earlier. I just added these methods into my reader object so it can return capsules instead of, well, the actual function. There's nothing fancy. It's just wrapping the function inside a lambda to return that. Right. That covers this particular micro optimization. Any questions so far? Yeah.
Are you familiar with the vector call calling convention?
Vector call calling convention of Python functions?
Yeah.
There is one, yes. That's the most optimized one, I know. So yeah, so there's a calling convention for Python functions you can choose where the C function you wrote just expects a pointer of PyObjects instead of like a more complicated data structure containing like named arguments and unnamed arguments and all that stuff. So yes, that would be faster. I haven't really explicitly profiled how much faster that is. It would still not be 10 nanoseconds or whatever. It might be 70 nanoseconds, 50 nanoseconds, somewhere in that range. Also, there would still be a conversion between Python and C types at the function boundary layer. If you had a raw C function pointer and you were writing Cython, you could get rid of all those overheads. It's just a tool. It's not really something that's the best, but yes, that the vector calling convention would offer some improvement over the performance of this code. Yeah. All right. Cool. Well, this is, I guess, the more generic part of this talk. Now we'll talk about some real stuff. I just wanted to talk about NumPy and see what those guys did. And maybe it can help us design our libraries better. What is NumPy? For people not familiar, it's just an abstraction over contiguous arrays, especially multi-dimensional contiguous arrays. And it offers some helpful APIs in Python that allow Python users to do complex hot path operations over these, underlying contiguous C arrays, like np.mean. Here I have a very small example of this exact same thing. The Python user did not have to write a for loop over this. It just computed the mean for you. That function could internally be doing any sort of complex stuff. It could be doing SIMD if you wanted it to. And that's really nice. It's a nice user-facing API for dealing with contiguous data. This next few slides are based on some stuff I read about NumPy. Here are some links. But let's try to design this library ourselves and see if we can. If you had to design an ND array with 3 dimensions, let's say, not even a matrix, how would you do that? You would probably first allocate a big block of memory. And you have to decide the layout of this memory. Like, do you want it to be row contiguous or column contiguous? I forgot the exact term. It's been a while. You would probably store the number of dimensions you have. Maybe you have 3 dimensions, 4 dimensions, 2 dimensions. And you would also want to know the length of those dimensions. Also, the data type. Are the objects integers, floats? And then you would probably have some iterator on top of this. So that's exactly what the NumPy authors did. This is the underlying struct behind the NumPy PyObject, the ND array PyObject. It's called PyArray object. Everything here is stuff you would have done anyway with slightly different types, except the stuff at the top, that's PyObject head. That's just how a Python object, a C struct that's compatible as a Python object, that's what it needs to do. It needs to have a head thing. That's a struct that contains a reference count of this object, and it contains a pointer to the type object of this object. And a type object, if for lack of a better parallel, you could think of that as a vtable. It's significantly more than that, but let's say if you were writing a class and you wanted with virtual functions, it would have a pointer at the start that's like the virtual function pointer table, virtual function table pointer that would contain pointers to all the methods defined on this class. So yes, that's also contained in that PyObject head. But that's the NumPy ND array struct. It contains the data pointer, it contains the dimensions, their strides, everything. So yeah, that's pretty much it. This library then implements various complicated functions that operate on the struct and give you the return values like mean. It probably vectorizes most of those functions, especially if you link like MKL and all those libraries in there. Usually you use this to do C-like operations on, let's say, matrices inside Python. Float, double, integers in 64. It has some other names for these types, but pretty much that's it. The takeaway. someone decided to implement ND array manipulation library in C. They made a nice DSL for it. Most people end up being able to use this DSL very conveniently. And it has lots of vectorizable methods that you can use. And what if we have a custom hot path that needs to return a big data structure to Python? We already saw this example. A NumPy array with, you can just populate that inside C and return that. Boost NumPy has bindings for this. I'm sure you can write this for any other system. Yeah.
PyBind has native conversions from eigentypes.
That's nice. Yeah. In this case, it's this thing, but yeah. Yeah. So none of these design decisions kind of focus on what the library, how to do something in a library. It's more of a matter of what are the concerns that we're thinking about when designing these things. Like, you could, let's say, use a library that magically does all this for you, but the day you have to tune that for performance, you need to think about these questions. So that's what I'm hoping to have as a takeaway from this talk. What are the questions we need to be asking? Here's my other example, which is a library I use pretty often. It's a columnar data manipulation API built on top of NumPy. It kind of adds more functionality to NumPy. Let me put it that way. Like, it's a very weak statement, don't hold me to it. But it just adds support for enums, timestamps, time differences, even Python objects inside like contiguous arrays, and allows you to write like efficient operations on top of this. It also lets you, create views out of this, let's say a matrix, a 2D matrix that you have, and do some time-based operations on it or something else. It's an even higher level DSL on top of just those contiguous arrays. It's just I call this a more advanced DSL. Higher level may not be the right term. Here's what these guys did. This is some snippet from a lib.pyx inside pandas. So the pandas authors actually chose to implement it all in Python, as you earlier alluded. That's actually pretty nice. Their code looks a lot like Python, but it's actually C. Anything that they want to use the Python's flexibility for, they just write it with Python objects if it's not critical enough. If they're doing some for loops, they just write it like this, and it converts to C loops. I'd say that's a very good design choice. They can also include other C headers from NumPy, for instance, into the scope of their Python program. That let them implement this widely used library, which for the most part is very performant. So they chose to write this in Python instead of using Boost Python, PyBind, all that stuff. Syntax is easy, interops are easy. Python is pretty nice in like automatically just like writing the conversions from C types to Python types, doing all the checks, everything. So why aren't we doing this? In my case, well, the builds were extremely complicated. I haven't tried doing that with CMake in a while. If you have a library, if you're very tied into that whole build system thing, you don't want to deal with figuring out Python, you could just build that as a .so and in your existing code using Boost Python, PyBind, or any other binding library, and expose those functions using the techniques we just saw. Or you could wrap your stuff with Python, and let Python do the compilation for you. Again, Python's compilation techniques might be limited, may not be. I haven't tried using CMake to compile Python. In my case, I could never get it to do like large cluster-based compilations, for instance, because my code needs like thousands of translation units. I haven't tried that. I'm sure someone could figure that out. Also, in my experience, debugging Python errors is not really like the easiest thing. It's easier to debug errors with C++. Python has sometimes inscrutable errors. But it's good to know we have options. And yeah.
You might get to this later, but how do you handle exceptions between these different layers? So like going from C++ to Python, or if you're also using Python, how can you raise exceptions back to Python, or I suppose handle on the C++ side or Python?
So from C++ to Python, we already saw the register exception translator function. Python automatically handles exceptions. It raises them to your Python layer if you call a Python function. You can register Python functions with it's not an attribute. You just like add at the end, you say except plus to say that it needs to catch exceptions. If you don't say that, then it doesn't catch exceptions, potentially for performance reasons. And well, that mostly crashes your interpreter if that happens. So usually do that in places where you do want to catch exceptions. I haven't tried raising an exception from C++ to Cython. Although, if that function that I had that was being used by Cython, if that function threw an exception and your Cython function was handling exceptions, it should have handled that exception because C raised it to the Python layer, and Cython is catching that. That said, I haven't tried that. Yeah.
If I might add, if you're raising an exception inside Cython code or something that is in that level,
yeah,
it will not propagate it to C++ code. So if you're using it there, it will not happen.
Yes.
So you will have to handle it. Your function inside Cython or whatever should catch it, and then throw an exception to C++.
Yeah. The other way would work. C++ to Cython to Python you can do, but Cython to C++ is something that would probably not work
You just need to handle it by yourself.
Yeah.
Just write a function in C++ and call it from Cython.
Fair enough, yeah. But yeah, overall, the reason I talked about the Cython thing is, again, even though we did not write any C++ here, and this is CPP now, it's always good to know what options we have, and maybe that helps us design better new libraries for the future that can make these things more seamless. All right, we're at the last and rather brief section. Some minor interesting stuff that I found while trying to build these modules. So going back to this thing. So this is the third time we're looking at this slide. One interesting thing it does is once you start returning NumPy arrays from your C extension module to Python, what you did is you tied the NumPy version or the NumPy ABI available during the building of your .so with the NumPy that's in the user's virtual environment inside their Python. If the ABIs are not compatible, this thing is going to be catastrophic. So how do we release such modules to prevent such issues? There's two schools of thoughts about this. Python has this thing called wheels. I'm not the most expert on this topic, but it's Python's way of creating like zip packages, let's put it this way, that are binary ABI versioned. Like you could create a wheel that says, hey, my this.so can only be used in a Python environment that has a ABI that's at least the minimum stable ABI that I compiled with, that I compiled my .so with. This works for NumPy. This works for the Python's internals as well, because you can't necessarily build something using the Python headers with Python 2.6 or something and then expect it to work in the latest Python. The ABI might have changed. You could write something, but not necessarily going to work. So wheels is the more canonical way to do this. The part that's more interesting as a C++ programmer is if you want the user to be doing a source build. Like instead of the user just downloading a pre-built .so for the exact version of NumPy, Python, and maybe 20 other dependencies that you have, maybe we can do something else. There's a nice Venn diagram that I have here. The user has some Python packages in their environment. Your C++ module requires some other dependencies. There is some intersection here. And I guess the two sections on the right, the brown and the orange one, are the ones of interest, because those are the ones we need to think about. So first, let's think about this thing. Any packages here need to at least be ABI compatible. So we need to ensure that much, at the very least. The approach I took here is I bundle a script with my source, whose job is to be invoked from inside the user's Python environment, parse out all the dependencies that they already have in their environment, and are also needed to build this package, and just pin the versions. Like I parse the current environment, and I set the version values to whatever the current environment has. And then I construct a C++ build environment and build this .so inside that environment. That brings us to this guy. Why did I do that? Why did I just not build it in the user's Python environment? Maybe it's a stable Python environment that's, not mutable, like not writable. Or maybe you just don't want to add conflicts into the user's environment just so they can use your .so. For instance, maybe I have boost here, and maybe for some reason boost 1.76 does not work with some package that they have in their Python environment. So just to avoid conflicts, I just get people to build, like, I just use this script to generate a separate environment and build my .so in there. This is the approach I've taken. I'm happy to hear better approaches. Finally, I also don't want to necessarily force the user to have the .sos that are needed for my environment to be built, for your extension module to be built. So some of the libraries like Boost, Protobuf, I just end up linking them statically into my .so to reduce the puzzle pieces even further, so things just fit together better. I guess now that's the last question in this talk, which is, do you know what would happen if you have two different extension modules, both, let's say, linking to two different versions of Boost, and some Python user loads both of them into their Python environment? Could there be symbol conflicts?
Symbol conflicts? I don't think so. Yeah. They're shared.
They could, not if they're shared, statically linked.
Or as in, because the separate modules are shared, and they only expose the initialization function.
Yes. That's because Python uses RTLD local. There are two ways to open .sos into your memory space. If you do that with RTLD global, there is actually conflicts. I have some examples I can show you later. I did try that out. But if you link two libraries statically, let's say you have two extension module 1, extension module 2, they both link to different versions of Boost. Loading them will not cause chaos. That's very helpful to know. That's because Python uses this thing called RTLD local to load these .sos into memory. So they don't really expose their symbols into the global memory space. I have seen one example of an open source library which somewhere had some code that modifies Python to do RTLD global. If by mistake you load that library, good luck. You should probably avoid changing this behavior. It's very helpful. It avoids unexpected things from happening. But most of the stuff we're only talking about, because we linked, I propose that we link some dependencies statically. There are only two use cases I could think of. One is the user is just not expected to have that library, like Boost. No Python environment would have Boost in it. Or your library is linking to that thing without an explicit RPath, or you don't expect libboost.so to be available on the user system. So you might as well just build it statically so they don't have to deal with the missing dependency of Boost as a Python user. But yeah, well, that brings us to the end of this. And I guess if there are any questions right now? Yeah.
So considering your example with the two subscription channels,
yeah.
If you split our Python layer to different modules, Python scripts, let's say, with each one just subscribing to one of the channels, do we still have to deal with the GIL issues?
How do you split? How do you propose splitting them?
Scripts, say.
Okay, different Python processes. Then there's no GIL involvement here. Yeah. So Python has this lock only for the same memory space because the Python objects cannot be manipulated. They're not thread safe, basically. They're internals. Yeah. Yeah.
You mentioned the DSL several times to reduce work in the Python code to move it to C or C++ code.
Yeah.
Is that DSL like Python abstractions that try to like construct work that must be done, and then when the actual library function ends up being called, is it like a lazy kind of thing?
Yeah, I think I should have expanded more on that. So DSL, by DSL, I just meant like domain-specific language. For instance, like you could say SQL is a DSL that lets you operate on the data stored in a database. You just construct what you want to do, and then some database library goes and reads the bytes and does that. Or PyTorch would be a DSL. You just describe the kind of neural network you want to train, and it actually goes and operates over the data repeatedly and does that. So that's what I meant by DSL, just a new kind of language, if you will, that might be more specific to that domain and solves the problems of that domain. It's not always to make a DSL without for. It's not always possible to make a DSL without for loops, which is why we tried that other pointer optimization. Yeah.
For NumPy, in effect, once you're in Python, how does it manage the arrays? It will be reference counting the main array all the time as you produce sub-arrays?
Yes, that's a very good question. It's here. So the Py object head internally contains a reference counter.
Oh, I
so
see.
whenever you get that object in Python, Python has to increment that counter. In C++, there is this boost Python wrapper around this NumPy array. It has like a smart pointer kind of semantic. It also increments that pointer. When you return this from C++, it decrements the pointer, but Python goes and increments it. So there's always like one reference to that.
So the C part of NumPy is specifically prepared for Python.
Yes. Yes. These two examples that I took, both these libraries are specifically written for the Python API. Yeah.
If you want to use it in C, it's problematic. I mean, not problematic, but you will have to have the reference count, even if you don't want to. Right?
No, you don't have to do that because C is not going to garbage collect it, right?
I see.
Yeah.
It ignores that part.
Yeah, I mean, you just have that as an object in your program, like this bpy, this result thing that I have. That'll just be an object in your program, and it does have this boost NumPy ND array wrapper does internally have smart pointer semantics. So if you destruct it, it will release the memory. But that's just the thing that Boost provided us on top of NumPy. I'm sure PyBind has some other abstraction for this.
I was wondering about that because I think it does do deterministic destruction.
Okay.
But it's if you ever just leave an object just out in the open, there's like you don't put it into any scope whatsoever.
Yeah.
It will just never get garbage collected.
Interesting. In Boost Python, like there's a wrapper called Boost Python object around every Py object, which does the reference counting for you. I find it easy to use. So
I think PyBind will do the same thing so long as it can get garbage collected.
Okay.
So I have a specific situation where we have a long-running Python interpreter, so that causes problems.
Okay, fun. Any more questions?
I have another one that this might be a PyBind 11 specific thing, but I don't know if you've heard of this. PyBind 11 will actually cast away any constants you have.
Okay.
So if you expose a reference to Python, theoretically, you could just do anything.
Okay.
I think that's because Python doesn't have the concept of constants.
Yeah.
So
no, actually, you can. No, not specifically that. What Python does is, let me open this thing. This guy.
Like you can't mutate name tuples.
Like this, I have this read-only thing. So at least this object, Python will not be allowed to mutate this ID thing here. And PyBind 11 does have a read-only.
It does, but so the specific situation. So like, for example, you can do, the only thing that prevents is you can't do assignment.
Yes.
But if you have like a .mutate,
oh yes,
it doesn't prevent that.
Yeah. Right.
One potential solution that I've read on the issue with PyBind is you can create two classes, a const version and a non-const version. And then the non-const version inherits from the const version. And the const version just doesn't have any of the methods that mutate.
Fair enough.
Yeah.
Okay.
It's not pretty.
Yeah, those are the kind of things that you deal with if you're exposing. Like basically, these are the kind of things you have to think about while writing something that was originally written for C++ and now being ported to Python. Someone just writing this thing from scratch, a library from scratch, meant for Python, probably would have made different decisions and not even thought of const in those situations. Yeah. But yeah, the target of this talk is people who have written C++ code and are just exposing. Any more questions? I guess we have time for one or two more. Yeah.
So instead of having all these problems with lifetime, is it possible from Python, I'm not an expert, to turn off the garbage collector for a particular object?
One way to do that is to keep a reference to that object inside your module somewhere in your C code. Before returning anything, you just like add it to some global dictionary that always keep a reference to this. Yeah.
There's no.
Okay. Yeah, go ahead. Okay.
So if I have a library for C++ that is kind of low level and I want to prepare it for PyBind 11 or Boost Python, what's the best thing I can do if I don't want to depend on those two libraries?
PyBind 11 is actually header only mostly, if I remember correctly.
It is.
Yeah.
Yeah, but still, I don't want to depend on that. I mean, I want to prepare everything so that somebody else can write the bindings as easy as possible without myself depending on the header.
So for the most part, everything we saw here, none of this, nothing in this row thing is Python specific.
Okay.
Yeah, they're very non-intrusive.
Yeah. You just write something on top of it. Usually what I have is I have all my code. Let's say I'll have a reader.h, reader.cpp, and then I just have a separate file, pyreader.cpp, which has all this code.
Having this Python head at the beginning wouldn't help in some sense. I mean, I can put the macro there, and if it's there, it will give the reference counting, things like that, but it's not very useful.
Which macro, sorry?
The py header, the py head.
In the struct?
Yes.
Oh no, so that part is done automatically by this library for you.
Okay.
Yeah, you don't have to write all that code. It's a NumPy.
But in my library, should I put that or not?
No. If you're using PyBind 11, let's say. Yeah. I guess we're out of time, right? All right, thank you so much, everyone. Yeah.